Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 30. And this problem asks us to first draw the 14 constitutional isomers with a molecular formula of C8, H9, Cl. And in B, it asks us to name all compounds that contain a trisubstituted benzene ring. And C asks us for which compounds are stereochemistry possible. Draw out all their stereoisomers. So let's start with A. So 14 constitutional isomers. So these can differ in their bonding and orientation in 3D space, but they must have the same molecular formula. And it must contain a benzene ring. So let's start with a benzene ring. So that's 6 carbons, 6 hydrogens. And we need 2 more carbons. That's 1, 2, and we need chlorine. So this is one option. Another one building off of that is something that looks like this, but now the chlorine's coming out of the middle carbon. Or, for example, we can alter the substituents. So, for example, I can have 1 carbon here in the chlorine, and the second carbon pair it to that. Or I could have 1 carbon with the chlorine, and then the methyl group ortho to that. Or I could have something that's like this, that I have those 2 carbons, and then I can have the chlorine meta to that. Or I could have the benzene ring with 2 carbons and the chlorine ortho. Or I can have the structure that looks like this and this, 1 carbon, 1 chlorine, but now the methyl is now meta to that. Or I could have something that looks like, the question also says that we need something tri-substituted off the benzene. Oh, that's what happened there. I could draw something tri-substituted, so I could have a methyl here, and a chlorine here. Or I could build off something like this and have the chlorine para to that ethyl group. And I have a chlorine para to that ethyl group. Or I could build off something like this and have those 2 methyl groups on adjacent carbons, such as this, and the chlorine right next to them. Or I could have those 2 adjacent methyl carbons with a gap carbon before we get to the chlorine. Or I could build off of this and I could draw the 2 methyl groups, but now with a gap in between them, and then the chlorine. Or I could build off of this and draw those 2 methyl groups with a gap in between, but now the chlorine is exactly opposite of them with internal plane of symmetry. Or I could build something like this, that I have a methyl, a gap, a chlorine, and then another methyl. So how many is that? It's 2, 4, 6, 8, 10, 12, 14. So this is the 14 possible constitutional isomers with this molecular formula. So they all differ in their bonding, but they have the same chemical formula. So that's part A. Now part B asks to name all compounds that contain a tri-substituted benzene ring. So let's identify a tri-substituted benzene ring. So this has 1 substituted, 1, 2, 2, 2, 2, 2. This has 3, this has 3. This has 3, this has 3, this has 3, and this has 3. So let's name these. So let's start with the most left one. So we'll start with our parent chain, which is the benzene ring. And then we can add the substituents in alphabetical order. So we know that our methyl group is going to be carbon number 1 because we could actually name this as toluene because toluene is a benzene with one methyl group coming out of it at carbon 1. So, but we'll just name it for benzene for consistency's sake out of all these. So we'll say this is carbon 1. That means chlorine is carbon 2 and the other methyl is carbon 3. So in alphabetical order, we have a 2-chloro, and then we have a 1,3. How many methyls? Dimethylbenzene. And that's for this one here. I'll actually put the name up there. That's for the most left one. And now for this one, now this time it's a little different because, oh, there we go. So now for this one, if I were to name this one, we can also name this as a toluene group with a methyl at the ortho position and chlorine at a meta position. So let's actually go ahead and name it like that just to see how it would look like. So we have toluene as our parent chain. And then one of these methyls will be the carbon 1. So then these are the ortho, these are the meta. So we have an M methyl, and then we have an O chloro. Then we have an O chloro M methyl toluene. But another way to name this, being consistent, is that we could just name this as a 1-chloro 2,3-dimethylbenzene. And now, what about this substituent here? So this one, if once again the methyl is carbon number 1, then we have a 1,2-dimethyl and then 4-chloro. So we have a 1,2-dimethylbenzene. But then remember, C comes before M, so chlorine comes first. So 4-chloro 1,2-dimethylbenzene. For this one right here. So alternatively, we can name this one. Oh, let's go. There we go. So let me put some arrows so we're not confused with all these names. So this is this. This is this. One. Nope. That's not right. So we have the 1,2-dimethyl, and then we have this one, which has actually both of these names, and now we're on this one. So let's actually start with this last one here. So here we have a 1-methyl, 4-methyl, and a 2-chloro. So if you remember, you always want to count so your substituents are on the lowest possible number. So if you count 1, 2, 3, 4, then chlorine's given carbon 2 instead of counting 1, 2, 3, 4. Chlorine would be given carbon 3. So we have a 2-chloro 1,4-dimethyl benzene. This is for the very last one, and now the second last one. Now we can name this like starting from the chlorine. Now we could possibly start from the chlorine and work our way around. We could have a 1-chloro-3,5-dimethylbenzene. So that's for the second one. Second last one. And now for this last one, once again, I can also start from the chlorine here. So we could have a 1-chloro, 2,4-dimethylbenzene. For this very last one. And now part C is asking for which compounds are stereochemistry possible, draw the possible stereoisomers. So stereochemistry occurs on chiral center. So a chiral center is a carbon center that has 4 different substituents attached to it. So let's look at, for example, this carbon here. Well, this carbon has double bond to another carbon, 1 bond to hydrogen, 1 bond to another carbon. So it has 1, 2, 3 substituents only. This double bonded carbon counts as the same thing. Also, this carbon here has 2 bonds to hydrogen, so it's not possible to have 4 unique substituents bound to it. If you work your way through all of these, you'll be able to determine that none of these carbons that have double bonds can be sp3 carbons. Therefore, it cannot be a chiral center. Its chiral center has to have 4 things attached to it. Therefore, it must be sp3. We know the alkene carbons are sp2. So none of these carbons on the benzene ring can be chiral. Only the ones that are on a substituent. But all of these carbons, for example, here have 2 hydrogens. If you work your way around, the only structure that doesn't have 2 hydrogens attached to 1 carbon is this structure here that has a chlorine, a hydrogen, a methyl, and a benzene substituent. So we can draw this in terms of 2 isomers, one having the chlorine coming out of the page as a wedge, and one having the chlorine coming into the page as dashed lines. So I can draw the chlorine now coming into the page as dashed lines. And now the proton will be coming out of the page. So remember, if you change the orientation of any 2 substituents, you will invert its stereochemistry. So remember, you have 2 bonds that are in the plane of the page, drawn just as bonds. Then you have to have 1 wedge, that means it's coming out of the page, and 1 dashed bond, meaning it's going into the page. And by switching the substituents of the wedge and the dash, you will invert the stereochemistry. So now the proton, instead of going in, is now coming out. So now we drew all possible stereoisomers. One is going to be R, one is going to be S stereoisomers for this chiral product here.